So the solution to the problems of the Big Bang, the problems presented by the Big Bang, is the theory of inflation. So we're not actually doing away with the Big Bang theory, but we are adding something very, very significant to it. We are adding this very early, very huge expansion that wasn't predicted by the original Big Bang theory. So inflation is an add-on, and it is a very rapid expansion of the universe at super early times, extremely early times. So here we're not just talking about the rate of expansion of the universe changing from what it was in the past. We're talking about it was crazy fast expansion, very, very briefly, very, very early, and then it went to sort of the normal Big Bang expansion. So at this time, and this is kind of cool and weird, space expanded faster than the speed of light. And this is really the key to solving the horizon problem. Space expanded much faster than the speed of light. So hopefully you're saying, I thought nothing could go faster than the speed of light. True. No thing, nothing, no mass, no matter, no light can go faster than the speed of light, but we're not talking about a thing traveling through space or energy traveling through space. We're talking about space itself. So the idea is here that during this early inflation period, space itself, space-time, right, 4 dimensions, expanded faster than the speed of light. Light wasn't ever traveling faster. The matter wasn't ever traveling faster because that was within space. It was the expansion. It was the stretching of the rubber band underneath the paper clips, right? It was that expansion that was much, much faster than the speed of light. Okay? So take a look at these pictures and notice here where the horizon is. Okay, because we're going to start talking about solutions. I'll come back to this. But in a normal Big Bang expansion, here's the horizon. In an inflationary universe, the horizon is within the major size, the whole size of the universe. We'll come back to that. Okay. Let's take the flatness problem first, though, because, again, I think it's kind of the easier one. So inflation provides a solution to both of the problems. Provides a solution in that it both smooths and flattens the early universe. It smooths it, which helps with the horizon problem, and it flattens, which helps with the flatness problem. So it smooths and flattens the early universe. Okay? So, let's take the flatness first. Think about any shape that you want. My picture here shows a sphere. But think about any shape. A triangle, a rectangle, a saddle, something. And make it huge in your mind. Blow it up and blow it up and blow it up some more. Any initial shape, lumpy, whatever it is, any initial shape, initial geometry of the universe that it had will look flat when it's inflated. And this is sort of about perspective, because what we have to remember is that I didn't get bigger when the universe inflated. The galaxies and the stars did not get bigger. The atoms So the universe is getting bigger underneath me. So when I look around and I used to see a sphere, now instead I see flat. Because I'm still small, so to speak. Think about the Earth, right? The Earth is a sphere. We've learned this. We're not flat earthers here in astronomy class. But when we look around us, we see flat. We don't see the curvature of the Earth because the Earth is so much bigger than we are. That's the idea here, that we can flatten any geometry by blowing it up huge and keeping our own perspective relatively small. Okay, so flatness, got it. Let's get back to this horizon problem and the smoothing part. So hopefully the flatness and the smoothing kind of goes together, but how does this have to do with the whole temperature and the horizon and blah blah blah? Well, what this does is when we inflate, remember we stay small, universe got super big, that means we can't see the whole universe. Big Bang sort of implies that we can still see everything, that it just goes at a rate where light can travel and keep up with it. Inflation says, no, we can only see part of the universe. We can only see a smaller horizon. Just like when you look around you today, you can only see a small part of the Earth. You can only see up to your personal horizon. So it makes sense then that what we see, so the universe we see within our horizon should be smooth. Because within what we can see is where light has traveled, and everything that we see in our horizon was in fact in contact with each other. Okay, so because all was in contact to begin with. Okay, and I should say this all right here. Sorry, I should have added this in. All of that all is everything within the horizon. So everything that we can see, everything where light has had time to travel is within our horizon. But the inflation says there is a universe that exists outside of what we can see, that we are only seeing part of the whole. So look, I showed you this number one picture before that said that with Big Bang, A and B should be different temperatures because light hasn't had time to travel across the whole universe. With this inflation, what we're saying is that all that we can see is within our horizon. That light only had this far to travel. That's all that we can see. This is what we call the observable universe. And so within our little circle here, within our horizon, everything should be the same temperature. The CMB should be smooth. Everything used to be in contact. We don't have to worry about B over here. It can be different than A. We're just worried about what we can see. Here's this picture again, right? Here is our horizon. Everything here is the same temperature, just like we see with the CMB, and it is very, very smooth. But there exists this other part that inflated so big, light hasn't had time to get to us yet. Weird, okay? The universe is bigger than we can see. That's inflation. Here's one more analogy for you. And by the way, inflation is a theory, just like the Big Bang. We don't know if it is perfect or if we're still missing a piece. But Here's the idea in another analogy. We got our friend the ant again, nice and small. We put the ant on a golf ball. When the ant's on a golf ball, it can feel all the bumps and wiggles. It can notice that it's on a curved surface and that it's not a flat surface, right? But we inflate the golf ball to ginormo size, right? Here, we have made this golf ball earth size. Now, if you know a golf ball, it has all those little dimples in it. Well, our ant, standing on an earth-size golf ball, would not think that it was round, would think that it was perfectly flat, just like we do when we look around. And those dimples in the golf ball, look at this. Those dimples would be hundreds and hundreds of miles wide and less than an atom deep. We would not see anything but smoothness and flatness. We would not see all the bumps, the dimples. We would not see the curvature because we blew it up so big. That's inflation for you.